This video should set you up with a rough idea, or at least a baseline idea on how to draw Lewis structures. So before we actually get into the rules of putting them together, get a little bit of history on what's happening with these. Back when Lewis was first trying to put together how we would get molecules, we tried to understand something about patterns, which we've talked about within our periodic table. And one of those patterns that we noticed for early on, particularly in row 2 and row 3, is that we noticed that our elements get up to 8 total electrons, and that was it. And so Lewis went through and said, okay, well, if I'm going to build a molecule, what I want to do is now take 2 atoms and have them interact with each other. And the most likely thing that's going to interact between those 2 atoms would be the electrons, because the electrons are on the outside. We took this a step further and said, okay, well, it's probably just the outermost or highest energy electrons. So we reference these as the valence electrons as opposed to the core electrons. So your valence electrons are going to be super, super important when looking at Lewis structures. These are just the highest energy level electrons. Okay, and we'll talk about what we mean when we look at some examples here, but it's the energy level, not the highest energy level. Okay, there's an important distinction there. And so we notice this kind of pattern of 8. Well, we said, okay, well, what shape, because we're looking at three-dimensional objects here, what shape carries 8 points? What could I work with that potentially has 8 points? Well, he did a pretty good job in his geometry and trigonometry classes, and he noted that really cubes have 8 points. And so we said, well, let's go ahead and equate each atom to a cube. So if we pick, say, our first example, we've got H bound to H, we would look at the electron configuration for hydrogen, which is 1s1, and for another hydrogen, 1s1. Oops. And all we care about is the highest energy level. Well, the highest energy level for hydrogen is simple. It is 1s1. It is its configuration. So we then went through and said, okay, well, let's add the electron into my diagram. So really what we're saying is that the hydrogen nucleus is at the center of this cube. Okay, and we'll color code the other one. So we've got our hydrogen nucleus chilling out in there. And what he went through and did is said, okay, I'm going to put that electron, that 1s1 electron, on the outside of that cube. And I'll do the same thing on the other one. And by doing this, he then said, okay, well, what could happen is if I then grab this cube and I overlap it over here, eventually what I notice is that there is now a pair of electrons connecting up and forming now a bond. So one connection between those, that overlapping interaction, gives us a bond. Cool. Well, he said, okay, well, what happens if I scale this up? So if we move to, say, HF, if we move to HF, we're still looking at hydrogen with a 1s1 electron configuration. When we move to fluorine, officially our configuration is 1s2, 2s2, 2p5. This is a bit odd. As what you may have noticed is I only included the 2 energy level, and that's because I'm looking at the valence electrons. It's the highest energy level, so I'll ignore the 1s2. This means that fluorine comes in with 7 valence electrons. Okay, and that's going to be an important skill to be able to pull out, is be able to quickly find the valence electrons. Hint, hint, look at the periodic table, in particular the the column number associated with it. If we go back through, because it's going to be easier to color code the hydrogen now, and draw in our single electron with our hydrogen, there's our electron, and with fluorine, we can go through and do the same thing, except now there are 7 electrons that have to go in. So I'll go through and put these electrons on each of those points. And sure enough, what happens is I end up with a vacancy at one spot, which then means, what can I do? I overlap those, or that side of our cube, and there we go. We've now got a bond between hydrogen and fluorine. he continued to try and build this model out. So one of the other options is, instead of looking at, say, HF, relatively simple, we could move to carbon, and our highest configuration is 2s2, 2p5, which means I have 4 valence electrons. If we again draw our diagram of what's happening, we've got our hydrogen with 1 electron there, and our carbon, we would go through and start to scatter those electrons around this. And one of the things that he ended up doing was scattering them on kind of opposite corners first. Well, if we go through and look at this, there's a vacancy, there's a vacancy, there's another vacancy, and there's another vacancy, which means there are now 4 spots that carbon could accept electrons. Well, if we look at the formula that we end up getting for CH4, for methane, carbon can have 4 hydrogens around it. Well, why? It's got these 4 vacancies where that single electron from a hydrogen atom can now share and form a bond. Okay? So he used this information to help us predict and come up with structures. Realize that we're now looking at 3-dimensional cubes to represent everything, and as you might guess, this is going to be a bit of a tedious process, particularly if you've tried to draw any of these things out already. So instead of dealing with these things in cubes, we've now simplified our understanding, and we start to make some kind of simple approximations. So if we go back to our HF or our HH system, we would go through and say, here's my hydrogen, and I now scatter the next hydrogen somewhere around it. I don't really care where. And I now can represent what's happening with the sharing of electrons. One of the things that you'll notice is that we'll always end up putting the atoms in kind of this weird 90-degree system. Well, why a weird 90-degree system? Well, if we take a cube and we flatten out a cube, what do we have? A square. So when you are building your Lewis structures, really all we're trying to do is stick to Lewis's model and put our atoms on the face of a square wherever our center atom is. Okay? And deciding the center atom is tricky, so we'll deal with that later. If we then go through and put in our electrons, hydrogen came in with 1, the other hydrogen came in with 1, I now have a pair of electrons between those atoms. So as long as I have a pair of electrons, I then switch that. Instead of being a bunch of electrons, which can get very confusing, is I now can turn that into a line between the atoms. Well, what does that line now represent? Well, that line, whoops, that was a big eraser. That line represents a bond, or ultimately a pair of electrons being shared between the atoms. Okay, well, that one was straightforward, so let's switch that up to a more difficult one. Let's go to the HF. Okay, well, what happened with our HF? In the case of fluorine, we said we had 7 valence electrons. We'll put our fluorine here and our fluorine here, and we'll go through and do the same thing. Hydrogen comes in with 1 electron. Our fluorine comes in with 7. Whoops, that would be 8. You would think I would have learned how to count. And we go through and we again look at how we've set this up. So the hydrogen, I just put the fluorine next to it on one of those faces of my square. And then it only had 1 electron, there's nothing really to consider. But when we looked at the fluorine, notice how I put the electrons in. I put them in pairs on each face of the square. Okay? The exact order or location of those pairs isn't super important. What is eventually important is noting that we now have a pair of electrons between the hydrogen and the fluorine. This again means that I can then convert that into HF with now my bond between them. I will also have to go through and specify each of those pairs of electrons around the fluorine. Those electrons could now potentially do something. Okay? Maybe form a bond to something else. So I can't ignore them, I have to show them. Last example that we'll burn through really quickly here before moving on to all of our rules is if we went through and looked at carbon. Carbon, we had 4 valence electrons. Okay? We'll put our carbon down and our hydrogen. We had 4 hydrogens. Well, so now we've got an interesting dilemma. Where should I put those 4 hydrogens? Well, what we need to then decide is what is our center atom. The center atom in this case will be our carbon, and we'll explain how we determine that once we look at our rules. And we'll scatter our 4 hydrogens on the square of that center atom, of our carbon. Okay? Now that I've put in those atoms, I can now deal with my electrons, and I can go through and add my electrons in for each of these. Notice that I'm placing the electrons in a location that is aimed towards an atom. When we go through and do this, you'll notice that I have pairs between each of those atoms, so I can then convert those into solid lines, and I now have the Lewis structure for CH4. Okay? Kind of a neat little process. You'll notice that as we went through and did this, and as most people go through and show this, that we tend to associate the electrons with the atom that brought the electrons in originally. This is a false step. Okay? And we're going to talk about how to fix that in just a second. Okay? So, we now have our official rules. Everybody has a slightly different rule set for how they decide to teach Lewis structures. Okay? Particularly at our campus, and I'm sure every other campus has slightly different rules as well. Okay? If you are in my class, you must follow these rules. Okay? The reason being is that these rules allow you to identify probably the hardest and most important concept of Lewis structures, resonance, at the very bottom. If you follow the rules established by your textbook, resonance becomes virtually impossible to identify. That's a bit of a problem. Okay? Resonance is also probably the most important thing in organic chemistry. So being able to identify it and find it very, very quickly is a super important feature. Okay? The method that I'm outlining here, if you follow these steps, verbatim, all the way through, will get you to the exact same answer that everybody else is telling you how to do, except resonance will become obvious in my, quote-unquote, okay, obvious in my rule set, and it's not obvious in any other description that you may find. Okay? So please, take a second, pause the video, read these rules, and follow them. We'll look at a couple examples and some shorthand of this that doesn't show all the details in just a second. So again, please pause the video. You haven't paused the video yet. I was serious. Please pause the video and read all of these rules. Okay, I'm taking you at your word. Hopefully you have now paused the video. You're familiar with most of these rules, and we can now move forward to looking at some examples on this. So, when we go through to generate our Lewis structures, our very first step for all Lewis structures is to total the valence electrons. So, let's take a look at our very first example. Let's start with CF4. Okay, so I'm actually going to erase the things underneath it here temporarily. So, CF4. Well, carbon brings in 4 valence electrons. Fluorine brings in 7 valence electrons. But there are 4 fluorines, so I need to multiply that 7 by 4. I then total this all up to get my total valence electrons, which should come out to be 32 electrons. Okay, so I now have my total. At this point, ignore valence electrons. We have a total amount of electrons. I don't care how many electrons are supposed to be around any individual atom. According to valence shells, the valence rules are irrelevant. I now need to pick a central atom. Okay? The shorthand rule here is saying our least electronegative. Doesn't always work, it gets us pretty close. It's the least electronegative element that can bridge, meaning it can have multiple bonds. Certain elements can only have one bond. For instance, hydrogen can only have one bond. Most of the halogens can only have one bond. Okay? So those will never be our center atom unless we're forced into weird situations. So in this question, I have a choice between carbon and fluorine. Fluorine is my most electronegative, which then means carbon is the least electronegative. Okay, and I'm going to have to pause real quickly for my chem130 students. I apologize, I have not defined electronegativity yet. So at this stage in the game, what I would like you to do is ignore that term of electronegativity, and you can come back and adjust this later once we know what electronegativity is. And we're going to change that around to something else. Okay, something that we have talked about. The central atom will be the most, and I know we just switched it to most, metallic. Okay, and we will add our electrons to the least metallic. Okay, so our most metallic atom is in the lower left-hand corner of our periodic table. Our least metallic is the upper right-hand corner. Well, fluorine is our classic case of the least metallic. Carbon is a little bit further to the left, so that makes it more metallic than fluorine. Does not make it a metal, it's just saying relatively carbon is more metallic. Okay? So, central atom, carbon. Okay. I will then go through and place the other atoms on the face of the square around my fluorine, or around my carbon. So there's fluorine, 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 whoops, not a lot of space down there, and fluorine. Okay. Now the trick is to add electrons into the structure. Okay. The electrons need to get added to very particular elements. The elements that they will be added to first will be the least metallic, so the element closest to the upper right-hand corner on our periodic table. Okay. And we're going to continue to add those electrons into those elements until we have added in all of our total electrons. Okay. Which brings up kind of a question. So I can go through and start adding. Well, actually, let's pause for a moment there. Fluorine, all of them are identical, so it doesn't matter which atom I start putting the electrons on. So I'm just going to start putting them in. And I'm going to switch the color because I don't want you to think that these are being tied to either fluorine or carbon necessarily. Okay. So you'll notice that I will go through and put in only 8 electrons. I won't add any more than that. And the reason being is that we only have 4 faces of a square, and each face is sort of equivalent to an orbital, which means I can only fit 2 electrons there. Okay? So now that I've added 8 electrons to the fluorine, I'm out of places I can put it on that fluorine, so I'll move to the next least metallic element, which will be another fluorine, and I'll continue to add my electrons to each of those faces, okay, and then so on. And yes, you will find this gets a bit tedious with all the little dots that you're drawing, but you won't see fluorine very often. Okay? So I've added all my electrons in. So if we go through and counted this, we should get 32 electrons in my structure. Okay? And I'm going to erase my box now. So now what I will do is convert pairs of electrons that are between atoms into a line. So the only places I can convert into lines would be those pairs that were on the inside. The electrons out here are not between atoms, so I will leave those alone as dots. Okay? The next part of this rule set is when you run into potential issues. Hopefully you don't run into them and you don't have to worry about it. Okay, so rule 6 is satisfy octets by moving pairs. Okay, remember that what we are trying to do is make sure that we get 8 electrons around every single atom. So let's go through and look at our fluorines. Well, there's 2 on that face, 2 there, 2 there. There's also 2 on this face, which means that fluorine has a total of 8 electrons around it. Its octet is now satisfied. Okay? If we check all of the fluorines, you should notice that they will all add up to exactly 8 electrons. Okay? This is an important feature within our Lewis structures. Remember, the pattern that Lewis found was that we were achieving 8 electrons around every single element within our structure, or within our compound. And that's a lot of 2's, so I'm going to get rid of most of them. The issue that now pops up is we also have to verify that there are 8 electrons around the carbon. Okay? And one of your problems may be is that I counted the 2 electrons in those bonds for all the fluorines. Well, then how many electrons are around the carbon? Well, I can count that same set of 2 electrons to both the carbon and the fluorine. They are now being equally shared, which means if I count the electrons around the carbon, there are 2, 4, 6, 8 electrons around the carbon as well, which means my octet is satisfied for the carbon. This means I do not have to worry about step 6, okay? Because all of my octets are achieved. There's nothing to worry about. Okay? You'll notice that the next line of this says something about formal charge. For those, and there's a big cross through it. For chem130, you don't have to worry about formal charge. So if anybody starts telling you how to calculate formal charge, you can tell them, well, you should be nice to them, but tell them that you aren't responsible for it for this class, and they need to stop talking about formal charge. Okay? The next big thing to watch out for, I lied, I completely forgot. Okay, so ignore formal charge. So let's try another quick example before we make it more difficult, which I believe the next few ones are actually going to do up here. So let's take a look at those. Yeah, all of those are going to be more difficult. So let's take a look at a quick modification. Let's ignore those for the moment. We're going to do NH3. Okay. Well, back to step 1. Total the valence electrons. Nitrogen comes in with 5 valence electrons. Hydrogen comes in with 1. There's 3 hydrogens, so I must multiply by 3, count for the electrons from every hydrogen, total it, and I get 8 electrons. 8 electrons now need to make it into my structure. If we now move to rule 2, our central atom is the most metallic. We have a dilemma here. Hydrogen is further to the left than nitrogen. That would suggest that hydrogen is the most metallic. However, hydrogen cannot bridge multiple atoms. And we'll look at what bridging means here in just a second. That means that nitrogen must be my central atom, even though it is less metallic than hydrogen. So I can then scatter my other atoms around. Here's again where our steps are going to impact or kind of run contrast to what you typically see. I now want to add these 8 electrons, and I will start adding them to the least metallic atom. The least metallic atom in this example is the nitrogen, which means I will start putting my 8 electrons around the nitrogen. In the previous example, we put the electrons around the atoms on the outside of the structure. Well, now I'm putting the electrons around the atom on the inside of the structure. Okay? We can go back and forth. We just have to know why we're putting them in different places. The reason we put them in the different places has to come back to this metallic character. Okay? I've now put in my 8 electrons, so step 4 is completed. I'll now convert them into a line wherever I have electrons between atoms. Well, I have 3 sets of electrons between atoms, so there's my lines. You'll notice that I did not change that extra pair of electrons on the nitrogen because those electrons are not between atoms. They are only associated with the nitrogen. Okay? Rule 6, satisfy octets. Well, if we go through and take a look at the nitrogen first, we have 2, 4, 6, 8 electrons around the nitrogen, so it has its octet. But what about the hydrogens? Well, as we talked about before, we can count the bond for both of them. So there's 2 around this first hydrogen. Ooh, that's not 8 electrons. Before we panic and start trying to slide electrons towards it, remember, some atoms don't need an octet. Hydrogen is one of those atoms. It is happy with only 2 electrons, which means it has achieved its octet. I know, it's an octet and it's only going to have 2 in it. It's not actually 8, but that's fair game for hydrogen. Most elements will need to have 8 electrons around them. So our hydrogen has 2, the next hydrogen has 2, the next hydrogen has 2. We have all of our octets, which then means that rule 6 is done. I have no need to worry of formal charge. I now have the Lewis structure for NH3. Pretty cool. So now let's make it more difficult. What we'll switch to now is our NH4. Okay? And this does get a little bit more challenging here. So let's take a look at it. Whoops, that was kind of a mistake. There's our NH4. Okay? This is an interesting one because we still have nitrogen with 5 valence. We have hydrogen with 1 electron. There's 4 of them. And then we could total this up and we'd say we'd have 9 electrons. But you'll notice I'm not totaling it right away because there's one more thing we have to consider. We have to consider the charge on the molecule. This molecule is positively charged, as seen in the upper right-hand corner. If it is positively charged, what does that mean to the number of electrons? We had to have lost an electron, which means when I get to my charge, I will now need to subtract 1 from my total. If I do not subtract that 1, I won't be able to solve this problem. I will end up then with 8 electrons that need to go into the structure. It's a good thing I erased everything, but we'll go through it really quickly. We can scatter my atoms on the 4 edges. I can put in my electrons on the nitrogen first, being the most electronegative. I can then go through, much to your probably disappointment, and erase, turn those into bonds. I've satisfied my octet. The formal charge does kind of show up here. I do not assign it per atom. I will assign it for the entire structure. So I will put brackets and say that entire compound is positive. I don't care where it's positive, but the whole thing is positive. Okay. I personally will get very lazy, and so I will let you do this as well. You can just use that as your bracket symbol. Okay? And we've now got the formula for NH4. Last big example, assuming I can find the proper buttons. Our last big example will be the last one on that list, which we'll see here in just a second, which was, I believe, SO3. And actually, even before we talk about that, what would happen for OH minus? Well, we'd count the electrons for oxygen. We'd count the electrons for hydrogen. What do we do with the negative charge? How did it get negative? Got negative by adding an electron. We include that electron in our valence count. Last one we'll look at will be SO3. Okay. Sulfur comes in with 6 electrons. Oxygen comes in with 6 electrons. There are 3 oxygens. This gets me a total of 24 valence electrons that need to go into my structure. I will start with sulfur as my central atom. It is closer to being a metal than oxygen is. I will then scatter the oxygens on the outside of my sulfur. I will then start to add electrons to my oxygens first because they are more electronegative, or sorry, less metallic than sulfur. I should be up to 18, did I do that right? 8 times 3 is 24. Oh, never mind, I'm there. 24 electrons, I can count. So we've now put in all of the electrons. So we can then convert pairs into a line. And we would now have our structure. So we'll move to step 6. Satisfy the octet by moving pairs of electrons. Well, if we check the oxygens, check it for yourself, but you should verify that there are 8 electrons around each of the oxygens. The sulfur becomes a bit tricky. The sulfur only has 6 electrons around it. That is a bit of a rub here. So we have to deal with this concept of resonance. What we will do is move electrons to stabilize the sulfur. What we will not do is just add 2 more electrons, because then I'd be at 26 electrons and I have to be at 24. Right? So I have to get to the octet. So if we don't add straight up electrons in, we can move electrons. So one option is to take the electrons on, say, an oxygen and put them on the sulfur. So what's the result of that? I now have that pair of electrons on the sulfur. I still have my 24 electrons. Great. Sulfur now has an octet. What happened to the oxygen? Ouch. The oxygen now has 6 electrons. So we have the right idea. We want to be able to move the electrons, but we can't move them in such a way where oxygen loses complete control over them. So what we will do instead is move that pair of electrons in between the sulfur and the oxygen. So the result would look something along these lines. Okay? But if I go back to step 5, anywhere that I have a pair of electrons between atoms must be converted into a line. So there we go. There's my line. The natural recurrence out of this is now, what is the bonding structure for SO3? Well, the bonding structure is it has one single line, which was a single bond. We have a second single bond. That says single and that says bond. And then we have an interesting discovery here. We have 2 single lines in the same space. We will call that actually a double bond, because I have 2 lines in that exact same space. So it's now a double bond. So I can explain something about the bonding nature for this compound. Kind of a neat little deal. And this is indeed bared out in the actual molecule for SO3. Now we come to the next interesting question. I'm going to go ahead and have to erase all that. This is a relevant one for resonance. Okay. To satisfy the octet, what did I do? I moved electrons from that rightmost oxygen in to make the structure. Okay. And that worked. That satisfied the octet. But why did I move those electrons? Could I not have moved those? Or how about these? Well, it turns out, yes, I could have. Which means if you are asked to draw the Lewis structure of SO3, and this is where it gets fun, or not fun, depending on your opinion, if you provided this structure, which was the first one we drew that one a little bit messy, but it's there, okay, you don't get full credit, because that is not the Lewis structure for SO3. Because I could have just as easily taken the electrons from that topmost oxygen to have made this Lewis structure. Okay. Well, if I had provided that answer, and not the one above, well, I'm still only supplying one structure. Okay, so I need to supply both of these structures. Well, now I'm getting more credit, but not complete credit. To get complete credit for this, I would also have to draw that last structure here, where the double bond is now on that left-hand side. Okay. When we are dealing with resonance, our molecules are now frozen in space, and we cannot spin, flip, or rotate these, which means each of these 3 structures is different from the others, because the oxygen on the right in the first structure has a double bond. In the second structure, it does not. Okay? This is kind of a bizarre concept, but this is what we're referencing when we look at resonance. It's finding a way to draw multiple Lewis structures for the exact same compound. Bit of a neat little deal. Okay? It is involved in finding different ways to move the electrons within the structure. Some structures you can move the electrons in different fashions without changing the molecule. Other structures you can't. SO3 happens to be one where you can move those electrons around. To get full credit for this molecule or for this formula, you must draw all three structures. Okay? One last example that we're going to walk through really quickly here would be SO4 minus 2. Okay, so actually I'm going to take a moment here and tell you to pause and try and draw this out on your own. I'm going to be quietly, I'll pause the video as well, and all the answers are just going to appear here with the magic of my own pause. So magically popped up, there we go. We've got our general skeleton for our Lewis structure here. Wherever we have a pair of electrons, we can then convert those into a line to represent a bond. And we would end up with this as our first guess as a Lewis structure. We'd then have to draw in our brackets and say minus 2. Believe it or not, this is the correct answer for our class. And our class is Fundamental General Chemistry, for those of you that aren't in our class. This is an interesting structure. If you talk to a tutor or someone that knows chemistry, they will say that this is wrong. This is not wrong. Okay? What happens in the real world is some extra stuff comes in particular as it bears out to formal charge that we are not responsible for in chem130, where we can't go any further than this. That said, I am aware that this is our limit, and I am very clearly telling you this is where you would need to stop for this molecule. If you go through and continue where you generate a structure that has exceeded the 8 electrons around a center atom or around any atom, you will be marked wrong. Okay? Regardless of whether the rest of the world tells us that that is correct or not. You do not have the rule set to be able to exceed the octet. So do not exceed the octet. This is the correct answer for SO4 minus 2. Okay? So, what we could then move on to is what do we do with Lewis structures once we've got them. We could go through and look at the Lewis structure for CH4. Hopefully you guys are now wicked fast at drawing your Lewis structures. And you should end up with something looking like that. Okay? Well, that's a little small, so let me draw it a little bit bigger out here. The next part of this is then doing some interpretation. So if we look at the bond angles in here, what is the bond angle between the hydrogen, the carbon, and that hydrogen? Hopefully what you would see is as we've drawn it, is it looks like it's 90 degrees. And if we look over here, it's 90 degrees. And here, roughly 90 degrees. I'm drawing it a little bit weird, but it's roughly 90 degrees all the way around because we picked a cube as our shape, or our square. Okay. Well, this is kind of an interesting issue here. Okay. We've got equal bond angles apparently, and we would expect that because none of those hydrogens are different from any one of the other hydrogens, which means the bond angle between all of the hydrogens should be identical. If at any point one of them is different, that doesn't match our understanding of the hydrogens being the same. Okay, I know it's kind of a weird concept. So let's try it again. All of those hydrogens are chemically identical, which means when we look at the Lewis structure, our Lewis structure had better represent those hydrogens all being in the exact same environment. Which means when I look at the bond angle all the way around, I better find the bond angle is always 90 degrees in this case, because that's what my Lewis structure shows. Okay? Those of you that are particularly good with your trig or geometry may start to say, but Mike, what is the bond angle between those two hydrogens? Ah, good point. That is 180 degrees. Crap. All this time and effort that we put together to come up with this model to represent how these atoms bond to each other does not match what we would expect of our molecule in 3 dimensions. This means we need to refine the model. It's not that our model is wrong, it's that we need to add more information to it. Okay? That more information comes from something known as the valence shell electron pair repulsion theory, also known as VSEPR. Okay? What it assumes is that all pairs of electrons will repel away from each other to get as much space as possible. Okay? As long as we have equivalent electron pairs, we would expect the exact same bond angles between everything. Where we run into a further refinement of this is that we have something known as the electron geometry. We just look at, are there electrons? And then we also have something known as the molecular geometry, okay, which is where are the atoms. I don't care about the electrons anymore, I just care where the atoms are located. Okay? To tell that difference, I still have to realize that electrons are still occupying space, preventing atoms from being there. Yes, this is a bit of a bizarre thing to deal with. Okay? So if we look at some geometries, in particular the electron geometry, and I always forget to do this. Oh, it looks like I did fix it. If we go through and looked at some representative molecules, for HF, if we pick our center atom to be the fluorine, that's where our issue is. Can't pick HF. Let's pick NaH. If we look at sodium and hydrogen, we would have sodium and hydrogen as our structure. Well, what is the number of electron groups? Well, our electron group and our molecular group geometry comes around our center atom. With only 2 atoms, that becomes difficult to figure out our center atom, so let's pick one. Sodium. How many groups of electrons are around the sodium? Well, there's only 1 group, which means the shape is linear. Done. Okay? What happens if we say move to magnesium chloride? Okay? Well, now when I look at magnesium chloride, hopefully you'll notice that it's a little bit easier to find a center atom. We'll pick the center atom to be our magnesium, and we'll now decide on how many groups of electrons are around it. And we see 2 groups of electrons, and the geometry becomes linear. But wait, that doesn't look very linear. Okay? The reason it doesn't look linear is that what we drew was the Lewis structure. It doesn't matter where I place the atoms around our square and our Lewis structure. It becomes incredibly important when I look at the shape. So you have to be careful with tying shape, okay, to your Lewis structure. So within your Lewis structure, just look for your number of electrons. That tells you the shape. Okay? You can continue to work through the rest of these models, and you'll notice that we get increasingly difficult shapes. Those last 2, the number of electron groups, 5 and 6, you are not responsible for in our class. You are responsible for it in future general chemistry classes. So if you want to learn more about those, you can talk to me later about that. Okay? Your textbook or other things tend to have some nice images on what these individual things look like. Okay? So there's some general pictures giving you an idea of what those shapes are and how they kind of relate to each other. So, yeah. If we looked at CH4, we said our bond angles, at least in our Lewis structure, were all exactly 90 degrees. But if we went through and actually drew out our Lewis structure, we would see that what we've got is 4 electron groups The shape that we get is tetrahedral. The bond angle in a tetrahedron is 109.5. So the bond angle actually found in our molecule is 109.5. Lewis structure does not represent shape. The next question, because of course it couldn't get as simple as that, right, are all groups of electrons the same? Well, let's take a look at a simple example. If we looked at CH4, when we look at the number of electron groups, we would say 4 electron groups, and as we saw on the previous slide, that would say we have a tetrahedral carbon. If we look at NH3, we should end up with something that looks something like this, which again has 4 electron groups, which would mean we would expect a tetrahedral electron geometry. And that's exactly what it is. But the molecular geometry doesn't or distinguishes a difference between bonding electrons and non-bonding electrons. Because in the molecular geometry, I now only care about the atoms. Okay? But the atoms cannot exist in a space where there are electrons. So the electron geometry forces a molecular geometry depending on bonding versus non-bonding electrons. In the case of CH4, our groups of electrons were all in bonds, hence the line. So I have 4 bonding groups of electrons. What happens in the case of NH3? Well, I have 3 bonding groups and 1 group that is not bonding. Well, that is now going to change my shape. I can't be the same tetrahedral shape because I'm now looking at the atoms, not the electrons. The shape that comes out of this is now trigonal pyramidal. How do we know this? Whoops. Why did it... Well, that's what we were supposed to see there. We would move to our electron geometry, which was our first column. We then evaluate our structure and say, where are we? So for both CH4 and for NH3, we were tetrahedral electron geometry. For CH4, there's nothing to change because everything is the same, so we're still tetrahedral. For NH3, we now have 1 non-bonding pair of electrons, so we refer to that one as trigonal pyramidal. You'll notice that as we move further and further through this, it gets more and more difficult. Remember how I said you weren't responsible for 5 and 6-membered groups of electrons? You aren't responsible for their shapes either. Okay? So don't worry about those shapes. Tricky molecules. Okay, let's take a look at CO2. Okay? Again, you should be able to process this pretty quickly. Carbon's on the outside. Carbon on the inside. Carbon comes in with 4 electrons. Oxygen comes in with 6. There's 2 of them. I should get 18 electrons. Did I do that right? 16 electrons. I can add my 16 electrons to my structure. So there's 8. I'll move over to the other oxygen. There's another 8. Okay. I'll convert into bonds. I've achieved my 16 electrons, so I can't add any more electrons, but I've noticed that my carbon is missing its octet. So what I will do is move a pair of electrons from each oxygen towards the carbon, and I will now make that bonds. What is the shape that I would predict for this molecule? Well, what is our electron geometry? I will go to each face of my square and say, or ask, are there electrons? Are there electrons on this face? No? Okay. Are there electrons on this face? Yes, there's a face. Are there electrons on this face? No? Are there electrons on this face? Yes. How many faces had electrons? Only 2. Which means the geometry I've got is linear. I don't care how many electrons are in each of those faces. I just care, are there electrons on that face, period. Okay? That is why that becomes a little bit trickier. Your overall summary is outlined kind of here when you're looking at your shapes. Look for your electron groups. This tells you your electron geometry. You then have to evaluate bonding and non-bonding groups. This is found easily because your bonding are shown as lines and your non-bonding are shown as dots. Okay? That then allows you to interpret an individual shape. So when trying to determine shapes, use this slide until you have got it memorized. Once it is memorized, you don't need to worry about it anymore. Okay? So because it's super important, I'm going to take you back to the Lewis structure rules because I want you to look at those and spend some time really trying to nail those down and get those perfect. Okay? Total your valence electrons. Choose a center atom. Add the electrons to the most electronegative atom first. This is the biggest difference between my set of rules and anybody else's set of rules. Okay, add the electrons to the most electronegative. Okay, or until we actually figure out what electronegativity is, we will add them to the least metallic. Okay. Continue adding electrons until you've achieved your total electron count. Okay. At this point, I don't care if oxygen only has 8 or has 6 electrons around it. I need to get to 8 electrons. Okay. Once the total has been achieved, I can stop adding electrons, and now what I'll have to do is try and simplify. First, convert pairs of electrons between atoms into a line. We now have a bond. And then you can start moving electrons around to between atoms to satisfy octets. Okay. Resonance means that there were multiple atoms that could have supplied electrons, okay, to a center atom or to some other atom that didn't have its octet. Okay. Your formal charge must be written in the upper right-hand corner. Apologize for letting that video run a little bit long there, but hopefully you guys have it now figured out. If you got questions, feel free to ask when you guys see me, or ask your tutors or the sub when they show up.